we're not going to put your life at risk, okay, any more than, well, probably not as much as if you were driving your car. So, but we will do, stability control is interesting because you get to look at what the airplane does when it isn't, you know, in its sweet spot, so to speak. And so that's what we're going to do in this semester, is take a look at stability control. I'm a firm believer that to learn flight testing, you need to strap the airplane to your behind, okay? And I'm also a firm believer that really flight testing is the only place in aerospace engineering where you get the big picture. Like I say, I worked at Cessna as a design engineer, and I had this one little thing that I was working on, and I had a guy sitting next to me who at Cessna had the responsibility for designing the aerial refueling system for the A-37 little attack fighter that they made the T-37 out of. He was designing the aerial refueling system and the whole fuel system for the airplane. And he got crossways with the bosses and left the company and went to what was then McDonnell Douglas in St. Louis as a design engineer. And he wrote me a letter sometime later, and I learned that he was in the left inboard flap group of the DC-10. Now think about that a minute. He was in the left inboard flap group. He was a group of people designing the left inboard flap. So there must have been a right inboard flap group, right outboard, left outboard. You get the picture. You know, you didn't get the big picture designing a clip for the flap. Okay. So that's why I like flight testing, is I get the big picture of what's going on with the airplane. Anyway, okay. Book, I'm not asking anybody to buy the book, but here's the book. I do have copies if you'd like one. I had a good price. AIAA, if you're a member of AIAA, sells a book for $75. It's yours for $65 if you want a copy. So, anyway.
And for a penny more, you'll sign it.
And for a penny more, I'll sign it. I'll give you an autograph copy. I said we're going to fly. We will right here. We're going to put you in flight groups. And we want to, if possible, to be able to rotate folks within the airplane so you're not in the back all the time. So, you know, we'd like to do that. However, in stability and control, in performance, those of you who are in performance, we generally kind of went with whatever CG came out. Normally the FAA requires that you do performance at the forward CG at maximum gross weight. And of course we weren't able to do that. In stability and control, we will have to move the CG positions around because the center of gravity plays an important role in stability and control. So, you know, sometimes you heavier folks are going to have to sit in the back to get the FCG. Sometimes you'll be in the forward to try to get forward CG. And we do have some ballast that we can shift the CG around. So doing the weight and balance before the flight will be important because each group will need to have a different center of gravity of the airplane, okay?
I'm going to pass this sheet around and exactly what the topic we're talking about. I want you to put your name, a good phone number to contact you.
That gets passed around. And when we talk about stability and control, we have to talk about an axis system, and there's several different axis systems. The first bullet up there, or first bubble, or whatever you want to call it, is axes that are fixed to the airplane. And there's two or three. We're going to deal primarily with the body axis, okay? And the body axis is fixed and it moves with the airplane. Some of the other axes, like the stability axis and the wind axis, they consider where the relative wind is to the airplane. That becomes the X direction on those. But we won't use those for most. We'll stick with the body axis primarily. However, when we do dynamics, we have to use another axis system that's not related to the airplane, because if we're using the airplane's axis system and we do a dynamic maneuver, the axis system's moving with the airplane, so that ain't gonna work. So we have to have one that's someplace on the earth. The inertial axis, generally, I think on the inertial axis, most folks consider the center of the sun as the origin, and the whole universe is kind of on that one. Earth axis, there's again on the Earth axis, the center of the Earth is the thing, and the one that we tend to use in flight test we call the flat Earth axis, and it moves with the airplane. Okay, it's, again, the x-axis is in the direction the airplane is moving. The y is 90 degrees to that on the Earth's surface, and the z is vertically up to the airplane. But the origin and the whole axis system moves with the airplane, and then you can relate motion of the airplane to another axis system. And so we'll be using that when we deal with dynamics. Stability control itself is a study of motion about one or more of these axis systems, and so that's what we're going to be doing. Now, I'm going to jump right into the equations of motion, but you'll find that we won't do a lot of stuff with the equations of motion, for the most part. But the equations of motion can all be derived from Newton's second law. Now, I tend to believe that if you know Newton's second law and you're a good mathematician, you can derive about anything you want in engineering. You don't have to know too much more. If you're a good mathematician, you can derive things with Newton's second law. But the equations of motion for an airplane, there are 3 linear degrees of freedom with corresponding equations, and where the force here is an externally applied force to the airplane, and the linear momentum, mass times the velocity, change with time. That gives you 3, and then there's 3 rotating degrees of freedom that correspond with the same thing, where G here is an externally applied moment, and H is the angular momentum of the whole thing. Well, with some mathematics, you can derive that. Here is one of the axis system, the body axis system. Again, the center of gravity is the origin for the body axis. Vertical axis points toward the Earth. Longitudinal axis is along the line of the airplane, and forward is positive. A moment about the longitudinal axis is a rolling moment, and we abbreviate that with the letter L. The y-axis or lateral axis is out the wings, and right is positive, and a moment about that axis, nose up being positive, okay? And the vertical axis is a yellow moment about it, and right is always positive on these systems. Okay, back to the equations of motion here. If we start with those previous 2 equations, and I probably should have moved those slides around, But if we start with those previous two equations, we can derive the 6 equations of motion. Here's the longitudinal equations of motion, or motion about the y-axis. Okay? And we have 2 linear equations and 1 rotational equation. Now, generally on these things, we can almost, for a good first start, we can ignore all the stuff to the right of that first term if we want to just get an idea of what the motion is going to be like. Okay, so here, here's the mass of the airplane times the acceleration in the x direction, which is u dot. Here's z, okay, force in the z direction, mass times the rate of, essentially that's the rate of climb. W dot is the rate of climb of the airplane. This is a pitch rate times the moment of inertia about the y-axis. Okay. All of these other terms are kind of cross-coupling terms. I say the reason you can take them, particularly longitudinally, you can kind of ignore everything to the right of that first term is because longitudinally not a lot of stuff's coupled. We won't be able to do that on the next set of equations, which is lateral directional. The airplane is designed to fly straight. When you bank the airplane, you also generate side slip. Or when you push on the rudder of the airplane, you generate side slip. And the airplane is so designed that it will also roll when you push on the rudder. So these equations of motion tend to couple. And what you notice here is, first off, the last set of equations, there was 1 linear equation, or 2 linear equations and 1 rotational equation. Here, we've got 1 linear equation and 2 rotational equations. So it tells you that lateral directional motion is going to be different. And so we'll talk about that. Again, first cut, you can ignore some of this stuff, but only, only about small angles. Well, the left-hand side of all these equations represent the aerodynamic forces and moments, and if you see these things in their full-blown form, they're much larger than what I've put on this slide. So the left hand's the forces and moments applied to the airplane, while the right-hand side represents the airplane's response, what the airplane does, okay, when those forces and moments are applied. Very important thing here. I see too many folks trying to solve things that are way away from the trim condition using the equations of motion. These are nonlinear second-order differential equations for which there is no known classical solution. I repeat that. Nonlinear second-order differential equations for which there is no known classical solution. Now, if you've taken courses in numerical analysis, we try to solve those with numerical analysis. And we can do it to a degree, okay? Trouble is, I see people who ought to know better taking those equations to trying to use them for extremes, and it don't work. They can be solved over limited ranges by making a number of simplifying assumptions. And you may have heard about the word assume. When you assume something, you write that word and and divide it, makes an ass out of you and me. Okay, so be careful about what you assume, and that's what happens with these folks who are doing that. Here's some of the assumptions for solving those equations of motion. Rigid body. Well, for the Cherokee 6, that's not a bad assumption. It doesn't flex much. But some years back, the airlines had an airplane called the DC-8, made by Douglas. The DC-8, particularly the Dash 61 version, was a very long airplane. And I happened to get the very back seat in one day. And it was a pretty rough day. And you could see up the aisle to the cockpit door except when there was turbulence. And then the cockpit door would go out of sight because the airplane was so flexible. Couldn't make that assumption for that airplane. Today, the Boeing 787, fairly new airplane in airline service. If you see pictures of that thing in flight, the wings look like this. Pretty flexible wings, not necessarily a rigid body. Okay, all of a sudden you violated, with those kinds of airplanes, you violated that rigid body assumption. Okay, you got to use something else. Fixed Earth and atmosphere. Well, we can say generally the Earth is fixed, not necessarily the atmosphere. It gets pretty turbulent at times. Okay. Constant mass. Well, Cherokee 6, again, constant mass is probably not a bad assumption because the 260 horsepower in the Cherokee 6 doesn't burn fuel very fast. However, if you take a Air Force F-15 or F-22, the fuel lines for those engines are this big around. They're woofing gas like you wouldn't believe. That assumption doesn't hold very well, okay? That constant mass assumption. Exceed plane is a plane of symmetry. Most cases, Cherokee 6, that works pretty well. But again, you take that fighter and you hang 2 bombs under one wing and nothing on the other wing, and it no longer, you violated that assumption. Small displacement angles, and this one is where it really happens, okay, as far as violating those assumptions. Is that people will try to solve things that are at the stall angle of attack or even higher. That's not small angles anymore. And lateral directional, if you get more than about 2 degrees away from trim, it becomes very nonlinear. So over a couple of degrees, yeah, you can say this is fine, but 6 or 8 degrees, nah. Small disturbances from trim, and again, that can, it's fairly easy to violate that one. And then we linearize the equations by use of a Taylor series assumption. What I say here, one of the most common mistakes in use of the equations is violation of the simplifying assumptions. If you get into working someplace in stability control, please remember this lecture. Okay? Don't make a fool of yourself by taking things to extremes that you can't really solve. Okay. Call the flight test guys. Send them the flight test guys to do that. Okay. Stability control definitions. We have to have some definitions. We're going to talk about trim. Now, those of you who are pilots know that, hey, you got a trim wheel, right? A little trim wheel that you adjust to make the airplane so you can fly it hands off. Forces and moments in that case, you move something, you move a surface, so the forces and moments about the CG are in balance, or zero, okay? Summation of the moments about the center of gravity are zero. And stability can be defined generally as a sense of the moments generated when the airplane is displaced from trim. What happens to it when you displace it from that zero condition? And we're going to talk more about it. Two categories of stability. Static stability. What happens when you just move the control and hold it there? That's static stability. And dynamic stability is when you move the control and then let go of it. Okay? And each of these categories has three cases. Positive. You move the control and it tends to come back to where it was after you, if you let go of it, or it exerts a force on you, saying, I don't like this, I'm not in trim anymore. You know, the airplane is talking back to you, so to speak. That's positive stability. Neutral stability is you deflect the control and the airplane's real happy there. You can take your hands off and it stays there. Negative stability is you deflect the control and it just keeps going. Okay? Well, you can see we probably don't want either one of these for most cases. Okay. Static stability deals with the initial tendency. And that's an operative word. That's one of the foot stompers that will probably appear on an exam. Okay, so you may want to write that down. The initial tendency of the aircraft when displaced from trim. That's the definition. Well, here's static stability. Here's the, everybody probably has seen this example. The so-called ball in a bowl. Okay, we have this ball and it's, sitting in the bottom of the bowl and it's real happy there. But if we push it out of the bottom, it tends to come back to the bottom of the bowl. Gravity tends to bring it back. But if we put a ball on this flat table and we displace it, it'll stay wherever it stops. Okay, so that's positive stability up there, the initial tendency to return to trim. Okay, here there is no tendency to return, so that's neutral stability. And then if we take the ball and we turn it upside down and we set the ball on top, it may take us a while to get it exactly on top. It'll probably stay there until somebody blows on it. The wind blows it off the side, and when it starts off the side, it ain't coming back. It's going to be negative stability. So that's the static stability, the initial tendency. Dynamic stability, on the other hand, is how the airplane responds after the disturbance with the passage of time. All of those things, there was no time involved, right? But if we, push the thing off and it keeps going over time, rolls off the table or rolls off the ball and out into the... That's dynamic stability. So what happens with the passage of time? Turns out that there's three cases of that too, and we'll look at those in just a minute. But first, let me define a couple other things. Control. Now, when we say stability and control, we say that in one breath. Stability and control. They're opposites. A very stable airplane is not a very controllable airplane. And a very controllable airplane is not a very stable airplane. Okay? They're opposites. But a lot of folks seem to get that confused and think that, control and stability are the same. They're not. For instance, if you've got airliner, say a 747 or something like that, you want that to be a very stable airplane. You know, you want it to be like this room. Because, you know, Aunt Minnie is going on that airplane, and Aunt Minnie has never been on an airplane in her life, and she's scared to death. She don't want those pilots up there doing whifferdills, you know. You know, she wants it to be like this room. She don't want to know the difference. Okay, so she doesn't want that 747 to be very controllable. Just enough to take off, fly level, and land. But a jet fighter, one that's going to try to shoot down another airplane, you don't want it to be very stable because you worked the poor pilot to death. For instance, F-16, when it first came out, it had a side stick controller which did not move. Okay, it was just welded to the airplane. Didn't move, but if the pilot exerted force on the controller, there were strain gauges in the stick that sent the electrons back to tell the servos what to do with control. Trouble is, it wasn't very long before the pilots were coming back from a 30-second dogfight. Just their flying suits were just sopping wet from sweat. And the Air Force said, what's going on here? Well, the guys, you know, when they're in this dogfight, they would exert all the force they could exert and didn't know when they'd reached the limit. There was a limit, that, you know, but they would continue to apply force and it was just wearing them out. So they went back and they redesigned the control on it so that it moved just a little. Like an eighth of an inch or something like that. And then the pilots could tell when they had all there was and they didn't need to pull anymore. So, control, the ability to displace the airplane from trim. It's the opposite of stability. A very controllable airplane is not a very stable airplane, and vice versa. Well, we talked about static stability. There's two types. Stick-fixed static stability, which all airplanes should have, and stick-free static stability, which not every airplane has. The types are related to the control system installed in the aircraft. Now, fortunately for you all, our airplane has the kind of control system that has both types. Okay? Several years back, the Air Force was designing a new trainer. It never saw the light of day. Well, they built a couple, but they were designing a new trainer. And the flight test folks at Edwards Air Force Base, who were doing this, had never seen what's called a reversible control system and didn't remember how to test it. You guys are going to get to learn that. Two types of control system. One's reversible. The other one's called irreversible. A reversible control system is like we have on the Cherokee 6. If you get in the Cherokee 6 and you move the elevator control, for instance, and you look back at the horizontal tail, you'll see the horizontal tail going up and down. If you get out of the cockpit, go back to the horizontal tail, get a hold of the horizontal tail and look up at the cockpit and move the elevator up and down, you'll see the control wheel move. That's a reversible control system, okay? However, an irreversible system, you move the cockpit control and sure enough, the elevator moves and you get out of the cockpit, you go back to and you get a hold of it, and if you could move it, you probably can't move it, but if you could move it, the control in the cockpit would not move. irreversible. Most fighters and today most airliners have irreversible control systems. They're hydraulic or they're fly-by-wire or some of those other words that you've heard. Those are the kinds of control systems that most of those airplanes have. General aviation airplanes still have reversible control systems, although that is changing with the higher end, okay? Gulfstream, for instance, one of their new jets is quote-unquote fly-by-wire. So, you know, but we've got good old reversible control systems, so we'll get to see all of it. An irreversible system only has stick-fixed stability. But the reversible system has both stick-free and stick-fixed stability, and we're going to talk about what that means later. Stick-fixed static stability is related to control position, and stick-free static stability is related to control force. Now, it turns out, and we'll talk more about this later, it turns out that the pilot really needs both. And we'll talk about why. Dynamic stability can exhibit both oscillatory and non-oscillatory forms. Let's move to that so you can see these two things. Here is the non-oscillatory forms of dynamic stability. Notice that we've got displacement versus time. Here's positive static, where we displace the control and let it go and it comes right back over time. Well, here's negative, we displace it and it just keeps on going over time. Or we displace it, here's neutral, and it just stays where it was, you know, as long as we leave it there. Then we have these cases. The last ones, well, in all of these three cases, you have positive static stability, but maybe negative dynamic. For instance, here's this one. Positive static stability, initial tendency is return to trim, but it goes right on through. And with each oscillation, it gets bigger and bigger. When I was in Tennessee, we had an airplane that exhibited this in the power approach case. We would demonstrate this to the class and find that it only took about 2 oscillations before I would intervene and say, no, you know, you can't stall or you can't exceed the flap limits or whatever. But it had positive, and the FAA regulations, by the way, have no requirements for long period. This is long period dynamic stability. They have a requirement for a short period, which the reason they have a requirement for short period is that the short period is of such duration that the pilot can easily get into the loop and make things worse, okay? And we're going to talk more about all of that later. But anyway, that airplane would do that. Some airplanes, Saratoga will do this. We'll do dynamic stability in the class, and we'll displace the Saratoga from its trim condition, and I'll return it to the trim condition and let go. And it will do some oscillations which will damp out. And we'll talk about why. Some airplanes I've also seen that will, particularly the airplane that did this in the power approach condition, in the climb condition, would do this. It would just oscillate forever. Well, we said since control is the opposite of stability, one would expect to have some limit in both. And these limits are described by the aircraft center of gravity envelope. Okay, the aft center of gravity limit is set by stability, while the forward center of gravity limit is set by control. Here's a typical center of gravity envelope for a light airplane. CG moving aft. If we move the CG aft, we will get to a point where the airplane just meets the requirements for stability. And then that sets the aft limit. If we move the center of gravity forward, we get to a point where we may not be able to rotate the airplane for takeoff. That sets the forward stability limit. Performance sets the top. Okay, so last semester, those of you who are in the performance course, we were worried about the top. How much weight can this thing carry and still perform reasonably well? Stability and control, we're worried about these guys. And although if you go through a design course, you will do some weight stuff where you develop what's called a potato diagram. How many of you have done a potato diagram for an airplane? Any of you done that in one of your courses? Well, what it is you start out with the airplane empty weight and you add stuff and then you get it max and determine the max gross by all the stuff you add, and then you start taking stuff out. And the diagram you end up with looks like a potato. That's why it's called a potato diagram, okay? And, but the designers will do that, and then they'll say, well, we think we need this and this for, stability limit. We think our center of gravity ought to look like this. Flight test guys are the guys who prove that either the designers were right or they were wrong. Probably about 50-50. Okay. So, and again, that gets back to my point about the big picture. Getting to see the big picture in flight testing. Okay. Gosh, almost time for lunch. It sounds like it's absolutely pouring out there. About anything that we've covered so far. Yes, sir.
Going back to the reversible and irreversible, feedback of the controls, wouldn't it be, I'm not a pilot, but wouldn't it be more beneficial to have the reversible to feel feedback of what the aircraft's doing?
Yes, it is. Although it may be heavier and you have problems with reversible controls, sometimes with stretch and with friction. Okay? And pilot strength. For instance, when we started going supersonic, all of a sudden the control forces got so high that folks couldn't handle it, particularly in transonic and supersonic regimes. It just took too much force to fly the airplane. In fact, if you've read Chuck Yeager's book about flying the X-1, the X-1, they didn't know about this. And the only way he was able, when he went supersonic, the only way he was able to fly the airplane was with the trim. It had a trimmable stabilizer. He wasn't strong enough to move the elevator because it was like somebody poured the stick in concrete. All he could do was move the trim and fly the airplane. So that's one of the reasons, because as you go supersonic, what happens is that normally we say the forces and moment act about the quarter chord subsonically. That's pretty much true of an airfoil. Supersonically, the lift, the aerodynamic center moves to about 50% of the chord as opposed to 25. That gives this large nose down moment which the tail has to counter, and that's why it works. Otherwise, you know, I mean, reversible control systems are good things. We have to fool on the irreversible systems. We have to fool the pilot into thinking that he has a reversible system. We have to give him some feedback.